So the pickle blade square problem, the week 2 of the lab is still tomorrow, seems like, and probably most of you still don't have the LCD modules. You return it to me, right? So I'm gonna give it to you today, this morning, so you can work on that one. And also at the same time, I was looking at XADC, so you can start running this demonstration. You can see that I think on the course project website, open one of them. Here it's showing you a resources to run that first demonstration. Okay, so here's a link to the official tutorial of the XADC, and that's the source files. So make the connection like this. You can see the XADC is on the bottom left corner of the board. Show you here. This one. So here's the board, right? You can tell it's over here. So that's the XADC ADC inputs. And it's designed in the differential input mode. So it's taking in the difference between the two ports. You got 1, 2, 3, 4 channels. Okay, 1, 2, 3, 4 channels available at the GPL pin headers. So what you are looking at is you looking from the side, right? So these are the power and ground, and it's channel 1, 2, 3, 4. So 4 channels. So the inputs, when I was doing that demo, I did really quickly and it worked. I did it this way, just run a very quick demonstration. Like this. Okay, 8 signals, but these are channel 1, 2, 3, 4, and it's taking differential inputs, which means if you have a AC signal, you probably want to ground the other one. Okay, so it's like a signal minus 0 is still that signal. So you can see what I did is VCCs from the basic 3 board is 3.3 volts. I connected to the power line here and then the ground line. And you can see all these ones from the tutorial, they recommended that you ground all of them, so it's not giving any noises or interference to the signal port. So if you don't use it, just ground it. So you can see all these channels are grounded, so 0 inputs. But for channel 1, I put a 1 to 0.3 volts and another one to ground. So it's calculating the difference, which means it's inputting a 0.3 volts to the ADC for the demonstration. And you can see there's a typo from the official website. It's asking you to choose which one you're actually using, because the GPL on the board gives you 4 options. It's XADC 1, 2, 3, 4 channels, and it's letting you the example lets you choose the different channel using the switch. So there are 2 switches from the right hand side. It's the lower 2 bits. It's basically 1, 0. It's not 0, 1. So it's a switch 1, 0. These 2 positions. If you have a switch down, which is 0, 0 for switch 1 and 0, it's picking up channel 1, and so on and so forth, like this. Okay, and if you can see that since we are picking up channel 1, so eventually you should use 0, 0 for the 2 inputs for the switches. All right, so it's taking the ADC is taking in data from channel 1 if you put 2 switches both at 0. So run a quick demonstration using this one to get some partial credits, so you can demonstrate that the XADC works. Okay, and I also noticed the one thing here, very interesting, which may change our circuit a little bit, but not a lot of it. I was looking at the XADC's document. I probably found this last year, but I just forgot. can see is the range. So first it's a 12-bit. It's a 12-bit ADC. All right, and then can't find it here anymore. I read about the input range. It says it's taking up to 1 volt, which confused me a little bit. Can't find that anymore. Okay, we can also search for that. I remember there's a document just for the XADCs, like about 100 pages, about every single detail of the ADC. But you know, we don't have to get into the that much detail of it. But I can't find that official document anymore. But I just read about this, so you can see it's 1 volt reference. A little bit concerned, right? So anything above 1 volt will not be converted. So I think what's happening is, even though the whole system is powered up at 3.3 volts, but eventually there's an internal regulator regulates it down to 1 volt for the ADC as a VREF. That will be a pretty big change to our design. So eventually, the analog input cannot go beyond 1 volt. If we come back to our design here, remember we are setting up our DC offset at 1 volt, so which means the AC signal is going to swing around 1 volt. That won't work. So I have to change this to 0.5 volts. If this is true, right? If this is true. So in that case, it won't be a disaster because we can just change this resistor and make this resistor smaller and bring this down to 0.5 volts. It shouldn't be a problem, okay? But just let you guys know, okay? If you put a 1 volt DC offset and your AC signal is swinging around 1 volt, but the whole range of the ADC is 1 volt, it won't work. I have to reduce this voltage later. So that won't be a difficult task. So we just simply change the resistor here. So eventually, your amplifier, right? Your amplifier has a range of 3.3 volts, right? 3.3 volts over here. However, that DC offset is just at 0.5 volts. Okay, so you're expecting your signal swing around 0.5 like this. Just wasting a lot of range over here. So if you wanna, we don't have to change anything. I think it doesn't matter. It just looks a little bit odd. But the thing is, using 3.3 volts as a universal power supply is beneficial because that's directly from the. It's the same power supply for the IPGA board as well. Okay, so just instead of using 1 volt, we probably have to change it to 0.5 volts for the DC offset for the amplifier, right? If I find new things from this, I will let you guys know. But for now, I think we're fine. You know, just for you guys, you know, after we receive the parts, just to build that amplifier and try to monitor the analog signal from oscilloscope, and at the same time, after you finish the current Lab8 Part 2 and also the SPY tutorial, I think these are 2 assignments you haven't done yet, right? Okay, so finish this 2 and then move on to the XADC demo, right? So record the results, partial results from this demo for partial credits. If this works, to demonstrate that XADC works on your side, then it's partially done. Okay, so I'm going to give you the LCD modules because part 2 of the Lab8, I think it's asking you to display things on the LCD, right? It's asking you to do display the results on LCD. Very quick note here. So if you look at this one, that's a solution that I sent to you for Lab8 part 1, okay? The display module is a bit different from the one we have been using, but it's okay. It's just a decoder for the 7-segment display. You're gonna see eventually it's a decoder taking in ins 3, in 2, in 1, and in 0. These are the 7-segment display patterns. So the patterns are they come from the assembly code like this. Okay, because assembly code the instructions is outputting data in the pattern of the 7-segment displays pattern. Is a DP, I think. So you are asked to change the pattern from DP A2G to DP G2A for basic 3 board, right? Because example here from the assembly code, it outputs a pattern of DP, comma, and A2G. It's 8 bits. Its MSB is DP and the rest is A2G. Okay, it's for a different FPGA board, which is a Spartan 3. Since we are using basis 3, so we have to change it to G2A. So it's a task for you guys to make the change. The assembly code is given, so you come down here and change the pattern by looking at, if you need a 0, you need these LEDs to be on, right? So look at that and change the order from A2G to G2A and replace the bytes here. That's for you, okay? I think this is for task 2. You should have done that already. But so these ones are eventually being sent to the Verilog code and appear as these ports. Okay, these patterns are sent to in. It just passed on from DS3 210 to the ins. So this is a display module and directly having a connection from these to the 7-segment display, to the SEGs. Because this guy, if you look at the ins, right? So the display module, if you draw a box here, that's the display module. It's taking, so these are 8 bits for the in 3 to in 0. And there's a mux inside the display module, but I'm going to show you the mux really quick. So this is in 3, and in 2, in 1, in 0. So everyone manages one display unit of the 4 7-segment display units. It's just being managed in a little bit different way compared to what we did in the past, which is fine. So it's having 4 of them, and there's the mux. If you scroll down here, it's in the display. Let's see if I can find it here. Oh, it's this one. So you can see that it's using a counter in the display mux module. you can see that Q register n-1, n-2. So the Q register is a 18-bit register. Okay, it's a different way of counting things. This is similar to count max. So N is 18, and you can see Q register is 17 to 0. So it's basically 18 bits. So what's happening is for that counter, it has 2 bits here from, so the 2 MSB bits, and then you have the rest 16 bits. Okay, the rest is 16 bits. So whenever it starts counting, it adding a 1 to it, and eventually count up to 2 to the 16th for all these bits. After they finish the counts, this one got to carry out, right? You got a 1 here. That should make sense, right? It's pretty simple because it has 18 bits. These are the 2 MSB, and these are the 16 bits, right? So it counts at 100 megahertz. It's flipping this LSB. So keep flipping this guy, and until it finishes all the counts here, it gotta carry out. Okay, and when that so in the next round, it's gonna count from 0 again, and then whenever it finishes the 2 to the 16th counts, all right, it's gonna flip this one. So this one originally the first time it flips, it becomes 0 1. Next time becomes 1 0, and then 1 1. And then jumps to 1 1. So originally it was 0 0, right? For the 2 MSBs. So what this one does is it's looking at the 2 MSB bits, these two guys, and whenever it was 0 0, it assigned AN, which is enabling code for the 7-7 display, enables the one on the right hand side, okay, and send the data from the assembly code, right? The output from the assembly code and to the 7-second display. So it's actually enabling the one on the right and send the data to the 7-second display unit on the right hand side as well at the same time. And then whenever it reaches 0 0 1, whenever the MS2 MSB bits reaches 0 1, it's enabling the second one from the right and sending the data for the second one to the 7-second display. Since they are sharing all the data lines, it's a common castle. And then whenever it's 1 0, it does this. It's enabling the third one. Okay? But by default, it's sending data to the one on the left. So it's actually a counter. Why is that? It's because these are the 2 MSB bits. And it's counting towards this guy, right? Whenever it reaches this guy, it flips this bit. So it's basically the same code as when counter equals count max, right? Like what we did, and then do something. So it's creating a time delay for the scanning for the 4 units, right? It's scanning through every single one, so your eye cannot resolve it. Does that make sense? It's a different way of counting max, of a count max. It just doesn't have a count max parameter in here. So it's only looking at the 2 MSB of the 18-bit number here. So a quick question for you is, if I want to have a longer time delay for the counting, what can I do here? If I need a longer time delay for the scanning. So for this scanning mechanism, now it's counting towards 2 to the 16th. If I need a longer time delay, or let it count for longer period of time, what should I do? Let me give you an example. If I have 4 bits, okay, I'm looking at these 2 bits. I got 4 bits, okay, so I start counting. It was 0 0, right? And then it counts. So it's flipping this LSB at 100 megahertz. That's a clock from the system. It starts counting. 0, 1, 1, 0, 1, 1. What's next? Boom, this one got carried out here, right? Then what's these 2 bits? Resets. Okay? What's next? 0, 1, 1, 0, 1, 1. Boom. Carry out. Okay, so if you're only looking at these 2 bits, how long does it take to flip one of the bits here or to make any changes? It has to count from 0 to 3, right? Actually count for 4 times, because after 3 you have to count for 1 more time in order to carry out. Make sense? Okay, so if you have a 16 bits here, it's the same thing. You have 16 bits for the counting, and you have the upper 2 MSB as the indicator, as a one you are using as a case. So these are the 2 MSB bits, all right? It's counting. You cannot see it's counting because whenever this one flips, you see it's a case statement, right? So whenever the case changes, which means it already reaches to the 16th of count. Otherwise, it won't change. So the 2 MSB, in order to have these 2 bits change, like these 2 bits change, it has to count for 4 times. And for this case, it has to count for 2 to the 16th times. All right? So that's how it reaches these numbers and make the changes to the to which one you want to display. Okay, you want to turn on, you want to enable. Okay, so these are the patterns. So for your code, whenever you are editing, we're not changing anything to the calculation. So the assembly code is done. We're not touching it. It's already outputting that all these data here for you guys. It's already done, and that data is in the format of the pattern of the 7-segment display. Why? Because of this. Okay, we know it. We just hard code it. It's basically the pattern of the 7-segment display LEDs. So in order to let it represent the real number, for example, if it's for part 1, task 2 of the Lab8, we need a decoder to convert it back to binary. So which means for example, the pattern is outputting a 0, and we know the middle one is G, right? And DP, so let's turn it off, for example. So if it's G2A, it's gonna be 1 1 and 6 zeros as a code for the pattern to display a 0 here, right? That's DP, that's G, and that's the rest. So all the rest should be on. All the rest should be on, right? And so if you have a case of this, so you want to program your display module, so within your display module, write up a case statement. Okay, have another always block and write a case statement to figure out if you see this number, if you see this number, right? You want to give LED. That's for task 2. Okay, you want to give LED an 8-bit binary 0, right? So it's going to be 8 zeros for this case. Start decoding it because the instruction, the assembly, is outputting a pattern, but the pattern doesn't represent the binary. Okay, so if you are trying to display that number on the LED, you just have to do this. You have to decode it. So for this case, right? For this case, For this case, you are giving this number to LED. So in that case, you can take the data from here. It's already available, right? Just use these data. So it's basically like a case. In 0, you need probably need 4 decoders. Case in 0, if in 0 is that pattern, you are giving zeros to LEDs. So it's going to be the same for the LCDs. It's just a byte, right? Since you have done the LCD lab and the byte is available, if the byte is available, you should be able to find a way to send the byte to the LCD display. Just connect to the GPLs and so the IPGA module, the Verilog module has an interface with the vector, right? So it directly put that vector, which is a byte or the data, in there, and then send it to the Verilog module of the LCD display. Just integrate everything together and find out the interface. Okay, so who else don't have the LCD modules and displays? You don't have. Okay, I'll give it back to you. And you can use the rest of the time here to work on the LCD. It's for task 3 or the SPY or the XADC project. Okay. So Thursday today, in the lab this afternoon is the VLSI lab. We will work on the Virtuoso labs, right? So it's due probably in a few days. When is that due? So 1, 2, 3 is probably running out of the internet for some reason. Is that due today for the 1, 2, 3? Is that due today? Yeah, is it due today? Okay. There's a lot of things due today and tomorrow, and I guess the 3 to 7 is due later this week or next week probably. On Monday. Okay, so we will work on that. We have tomorrow the whole morning. I have office hours. You guys have 1 hour in the morning and then followed by office hours. So hopefully you can get 3 to 7 done as well. I'm gonna send you the link to tutorial 7 because that's the TSMC one. I'm gonna send you the link through Dropbox for that one. Okay, I can now post it to my website. Okay, I'll give the time to you guys to work on your assignments.